Hi, I'm Steve Tonneau from the University of Edinburgh. I'm here to present SL1M, a method for efficiently planning leg locomotion using convex optimization. This work is sponsored by the H2020 Memo project and has been achieved in collaboration with folks from LAAS CNRS, the University of Trento, and Ehwa Women's University. To motivate our problem, let's consider one of our example results. Here, you can see the Taïx robot from PAL Robotics walking on complex terrain. Obviously, the feasibility and the quality of the motion is primarily defined by contact timings and locations. In particular, in this work, we are interested in finding where to create them. At each new step, we have a discrete choice of contact platforms and an infinity of possibilities on each of those platforms. We want to address this combinatorial problem as efficiently as possible. Let us now consider the bird's-eye view of a slightly different scene, and suppose we want to compute the motion that will bring the Taïx to the other side of the platform. Our combinatorial problem starts with the selection of the first step. Naively, we decide to go on a straight line. We arbitrarily decide to start with the left foot and place it at the red position on the first platform. Similarly, assuming a cyclic motion, we now place the right foot at the green position. Now ideally, we would like to make our next step on the second platform, here. However, we need to account for the feasibility of our contact plan. This crescent approximates the kinematic constraints of Taïx. With the right foot on the green location, the center of the left foot must belong to the crescent to satisfy the geometric feasibility. It appears safer to backtrack our contact plan and place the first step a little bit forward. This allows for the third step to lie completely on the second platform. Unrolling our naive policy, we end up in a local minima. You probably saw it coming a while ago, but most algorithms will exhibit this myopic behavior as they only plan a few steps ahead. We thus need to plan the path to our goal globally, with as many steps in advance as possible. This is of course problematic when dealing with combinatorial problems. Backtracking again, after a few trials and errors, we may end up in this situation. We are at the border of the red stepping stones, however, we are not able to cross the final step. Again, our plan is not feasible. This time it is not because of geometric constraints, but because of the dynamics of our robot. To cross the gap, we need to reach the last stepping stone with enough velocity to jump. Dynamic feasibility must be considered as well. The issue is obvious in this dynamic situation. However, even when walking, we must continuously ensure that the robot can maintain equilibrium while following the footsteps. In summary, at each new step, we must choose a contact surface such that the motion is feasible and make sure that it allows us to make progress towards our goal. Let's formalize the contact selection problem. We assume a quasi-flat environment with n candidate surfaces. We also assume that the surfaces are convex. As a result, a surface Sj can be represented by a set of linear inequalities. At each new phase I, we also associate one footstep position Pi, and we plan for m footsteps. A contact point Pi is constrained to belong to any of the n surfaces. So for each step, there are n possibilities. For planning m steps, there are n to the power of m possible combinations. The number of possibilities explodes with the number of steps that we want to plan. Our problem can be written in the following general form. Find the variable x that comprises m contact positions such that the kinematic and dynamic feasibility of the plan is guaranteed, and such that the initial and final conditions of the problem are met. In our previous example, a goal condition is that the robot lies on the platform on the far right. The combinatorial constraint is that at each phase I, the contact position Pi must lie on either of the contact surfaces. This is our starting point. Let's see how we can try to handle the combinatorial efficiently. Handling the OR constraints usually involves solving a mixed integer linear program, which can lead to a combinatorial explosion. Our objective is to get rid of the OR constraint and relax this problem into a convex linear program. For this, we will assume that the feasibility, initial and goal constraints are convex as detailed in the paper. If a point Pi lies on a surface Sj, then this inequality is necessarily satisfied. As there are no overlaps between the contact surfaces, only one such inequality can be satisfied at each phase. But what if we wanted to satisfy them all simultaneously? We can introduce positive slack variables Cij, one for each contact surface at each phase. For an arbitrarily large value of Cij, the constraint will always be satisfied. On the other hand, if Cij is equal to 0, then necessarily Pi will belong to the surface Sj. We can use the Ci vector, which contains all of the Cij's, to draw a necessary condition for the point Pi to lie on a surface. If the number of non-zeros entries in Ci is less than the total number of surfaces, that is n, Pi is necessarily on a contact surface. This number is called the cardinality of the vector. Our surfaces are not intersecting, so we note that the minimum value is n-1. This shows that finding a point Pi on a surface is strictly equivalent to an optimization problem where we try to minimize the cardinality of the slack vector Ci. At the minimum, one of the Cij is equal to 0 if the problem is feasible, and as a result, Pi belongs to a surface. This means that we can reformulate our original problem here and remove completely the OR constraints. We traded the feasibility problem for a strictly equivalent minimization problem. Still, minimizing the cardinality of a vector is in fact also a mixed integer optimization problem. So it seems that we have not progressed that much. Fortunately, it is well known that the cardinality minimization problem can be well approximated as an SL1M minimization problem. The L1-norm minimization induces sparsity, which means that we can hope that some entries of the Ci vectors will be 0 at the end of the optimization. This allows us to reformulate a combinatorial mixed integer problem into a standard linear program that you see on the right. Unfortunately, while doing this, we lose our guarantees of convergence to a feasible solution. We will refer to the paper for a discussion on the handling of those cases. The main advantage of the approximation is computational efficiency. Our method is up to 100 times faster than the mixed integer formulation in the most favorable cases when also considering an additional objective function. However, the drawback is that the relaxation can converge to unfeasible solution, and handling those cases can reduce the computational advantage. Further research is needed to deeply understand the cases where SLIM is advantageous over mixed integer program. Another important point is the question of feasibility versus optimality. Rather than simply finding a contact plan that solves our problem, we may be interested in choosing a plan that will minimize a given cost functional. Under the SLIM formulation, this cost will be added to an SL1-norm minimization cost, which means that the optimum of the relaxed problem is unlikely to be the optimum of the original problem. Our early results indicate, however, that first solving the feasibility problem and then computing an optimal motion once the contact surfaces have been selected gives good empirical results. Here again, further research will determine whether the theoretical problem is also a practical one. Conversely, investigating the performance of the mixed integer program formulation when only solving feasibility and not optimizing the cost is another interesting direction of research. That's it for the presentation. I invite you to consult my website, stevetonneau.fr, for the paper, video, and source code. I will be very happy to take questions during ICRA or at any other time by email. Thank you very much for your attention.